Good day, sir. Good day, classmates. Good day, everyone. So, I am Maria Isabel M. Mallorca. I'm a second year student of BS Ed Mathematics from the University of Southeastern Philippines, Tagum Campus. And today, I will be the one to discuss to you about the graphing functions, extreme function values, and optimization, specifically the topic about the mean value theorem. So what is the mean value theorem all about? As stated in the introduction of to this chapter, it is one of the most important theorems in calculus. Why? Because it is used to prove many theorems of both differential and integral calculus, as well as numerical analysis. Alright? So the proof of the mean value theorem is a special case of the Rolle's theorem. So what is the Rolle's theorem? But before we dig into that topic deeper, we are going to discuss all about the learning outcomes for this video. So after the video, you will be able to develop understanding on the concepts related to the Rolle's theorem and mean value theorem. And also, you can now verify that the hypothesis of the Rolle's theorem and mean value theorem satisfied from the given function. And lastly, you could also find a suitable value for C that satisfy the Rolle's theorem and the mean value theorem. Okay, but before that, let's get started by you may pause the video for this if you want to join. So you may sketch a rectangular coordinate plane on a piece of paper, just like shown in this, the red color like that. Using like that one. Using a pencil or pen that you have, you can plot a point 1, 3 and 5, 3 and draw a graph from that point of a differentiable function that starts at 1, 3 and ends at 5, 3. Okay? You may pause the video if you want to join. Okay, so let's continue now. Let us think about what did you do earlier from the let's get started. So allow me to ask you a question. Is there at least one point on the graph for which the derivative is 0? Would it be possible to draw a graph so that there is not a point for which the derivative is 0? And explain reasoning. You may contemplate your answer now. Okay, so let us now explore what is the Rolle's theorem all about. So the Rolle's theorem, there is a French mathematician, namely Michael Rolle from 1652 to 1719 prove. So he was the one to prove that there is f. That if f is a function continuous on a closed interval a, b, and differentiable on the open interval a, b, and if f of a is equals to 0 and f of b is equals to 0, then there is at least one number c between a and b for which f prime of c is equals to 0. So that is what the French mathematician Michael Rolle told us. That so in other words, let me explain from the PPT or from the video. Rolle's theorem states that let f be a function, such as the first condition, it is continuous on a closed interval a, b. The second condition is that it is differentiable on the open interval a, b. And the third condition for the Rolle's theorem, if f of a is equals to 0 and f of b is equals to 0, therefore Rolle's theorem states that there is a number c in the open interval ab such that f prime of c is equals to 0. So let's take a look at this let's take a look at these graphs of some typical functions that satisfy the three hypotheses. What can you say about the pictures from the graph A to graph D? You may pause the video if you want to think more about it. Okay, so the answer is that it appears that there is at least one point on the graph where the tangent is horizontal to x-axis. Therefore, Rolle's theorem is plausible. Let's say, for example, for letter B, there is a one point that is tangent to the function that is also parallel to the x-axis. Let's have letter C for 2 points and letter D for 1 point. So let's give ourselves an example for further understanding of this theorem. No? So let's have a function x squared minus 4x plus 3 in the closed interval 1, 3. So our goal today is to verify the three conditions, if you still remember those, of the hypothesis of the Rolle's theorem on the indicated interval. Then right after, if it is satisfied, no, we should find a suitable value of c that satisfy the conclusion of the Rolle's theorem. If you want to participate, you may pause the video. Okay, so let's have the solution for the example number 1. The letter A. The first condition, because f is a polynomial function and it is continuous everywhere, thus f is continuous at the closed interval 1 and 3. So it's satisfied. No? So let's have the second condition. If it is satisfied, the f of x is equal to x squared minus 4x plus 3. If we're going to differentiate this function, we could have f prime of x is equal to 2x minus 4. Therefore, f is differentiable everywhere, and f is also differentiable on the open interval 1, 3. Let's have the f of a is equals to 0 and f of b is equals to 0 as well. So let's have f of x is equals to x squared minus 4x plus 3. Let's have x is equals to 1 or a is equals to 1. Let us substitute them. So f of 1 is equals to 1 squared minus 4 plus 3. And we could have f of 1 is equals to 0. Alright, let's have the b. The b is the x. b is equals to 3. We have f of x is equals to x squared minus 4x plus 3. We're going to substitute the value of 3. So we could have f of 3 is equals to 3 squared minus 4 times 3 plus 3 is equals to 0. So the third condition is satisfied, right? Next is that we are going to find the suitable value for c that satisfies the conclusion of the Rolle's theorem. So let us have f prime of c is equals to 2c minus 4. Let us set f prime of c is equals to 0. So we could have 2c minus 4 is equals to 0 using equality property, no? We could have C is equals to 2. Let us take a look at the graph, no? So, because 2 is an element in the open interval 1, 3, 2 qualifies as C. As shown in the figure below, 2 is a suitable value of C that satisfies the Rolle's theorem. So, that is the graph. So, the f prime of C is equals to 0 at one point in the closed interval 1, 3, which is the number 2. So, let us have another example. No? You may pause the video and want to join again. So, given the f of x is equals to x cubed minus 2x squared minus x plus 2 and the closed interval 1, 2, we're going to do the same process, verify the three conditions, no, of the Rolle's theorem, and also find the suitable value of C that satisfies the conclusion of the Rolle's theorem. You may pause the video if you want to join. Okay, let's go for the solution. So the solution for the example number 2 is that because f is polynomial function, no, and it's continuous everywhere, thus f is continuous on the closed interval 1, 2. Let us know if it is differentiable also. So f of x is equals to x cubed minus 2x squared minus x plus 2. So let us find rather the f prime of x using the power rule, the constant rule, the subtraction rule, addition rule, no? So we could, no. Sum and difference rule rather, no? So we could have 3x squared minus 4x squared minus 1. So f is differentiable everywhere, thus f is differentiable on the open interval 1 and 2. So let us have the third condition that f of a is equals to 0 and f of b is also equals to 0. So f of x, let us substitute the a, which is 1, to the function. So we could have f of 1 is equals to 1 cubed minus 2 times 1 squared minus 1 plus 2. So we will have here, here is f of 1 is equals to 0. So we have the f of p is equals to 0. So let us have the f of 2 right here. F of 2 is equals to 2 cubed minus 2 times 2 squared minus 2 plus 2. F of 2 is equals to 0, so it satisfies all, no? And then we could now proceed to our letter B to find a suitable value for C. So f prime of C is equals to is equals to 3c squared minus 4c minus 4c minus 1, such that f of c is equals to 0. Let us have 3c squared minus 4c minus 1 is equals to 0. So using the quadratic formula, or yes, the quadratic formula is we could have c is equals to negative 0.22 approximately, and c is equals to approximately 1.55. And then we're going to find which of the following, if the two of them, would be a suitable value of c that satisfy the Rolle's theorem. Let us see. C, because c is equals to 1.55 is the only element in the open interval 1 and 2, C qualifies, C approximately 1.55 qualifies only as the C. So we have, right, diba? We have 2 points which are negative 0.22 and 1.55 both approximately, only the 1.55 is an element in the open interval 1, 2, because the negative 0.22 is not an element in the open interval 1 and 2. So as shown in the figure below, no, approximately 1.55 is a suitable value of C that satisfies the Rolle's theorem. So f of c is equals to 0 at one point in the interval, in the closed interval 1, 2, which is the approximately 1.55. Okay, do you have any questions? You may leave it in the comment section, no? So we now apply Rolle's theorem to prove the mean value theorem. You should become thoroughly familiar with the concept of this theorem, the Rolle's theorem, so that because the mean value theorem is also called an existence theorem. Many concepts in mathematics are based on existence theorem or the mean value theorem. Let us have the example, no? The examples are the intermediate value theorem and extreme value theorem. So what is the mean value tells us? The mean value theorem tells us that there is at least one point on the graph where the slope of the tangent line is the same as the slope of the second line. In other words, there is a point, at least one point, where the tangent line, like this, like the tangent line, no? Tangent line is parallel to the second line. There are 2 points right here, which is the point 1 and the point 2 for the figure 4. For the figure 3, there is a 1 point, no? That is tangent to the function and also parallel to the secant line. So how we're going to find this out, no? How we're going to find that tangent line. So the mean value theorem tells us that let f be a function such that the first condition, it is continuous on the closed interval a, b, such parehas, just like the Rolle's theorem, and it is also differentiable on the open interval ab. Then there is a number in the open interval ab such that f prime of c is equals to f of b minus f of a all over f of b, no, all over b minus a. Sorry. Alright. So let us have an example to furtherly understand what is the mean value theorem. Let us remember that mean value theorem states that there is at least one point wherein the tangent line is parallel to the second line of the function. So let us have an example. Given that f of x is equal to x cubed plus x squared minus 2x, let us verify the hypothesis. How many hypotheses do we have in mean value theorem? We have 2. Is satisfied for a is equals to 1 and b is equals to 3. Then let us find a number c in the open interval 1, 3 such that f prime of c is equals to f of 3 minus f of 1 all over 3 minus 1. So let us support our choice later by graphically plotting in the same window or in our PPT later. I will show you, no, the graph of f that is tangent to the line at x equals to 0, c, and second line through the points f1 is equals point to the through the point 1 f of 1 and 3 f of 3. Alright. So you may pause the video on what if you want to solve for this. Now let's have the solution. So let us verify the hypothesis of the mean value theorem. There are only 2. So because f is polynomial function and therefore it is continuous everywhere, thus f is continuous on and the closed interval, right there, 1, 3. So, for the second hypothesis or the second condition of the mean value theorem, let us know if x cubed plus x squared minus 2x is differentiable. So let us find the f prime of x. So using the power rule, sum and difference rule, and also constant rule, no? The f prime of x is equals to 3x squared plus 2x minus 2. F is differentiable everywhere. Thus, f is differentiable on the open interval 1 and 3. Therefore, the two conditions are satisfied. The hypothesis of the mean value theorem therefore satisfied for any a and b. And now we can apply the mean value theorem to solve for c. No? So, let us first find the first derivative. We already find the first derivative, no? So, the first derivative is 3, right here. The first derivative of our function x cubed plus x squared minus 2x is equals to f prime of c is equals to 3x squared plus 2x minus 2. Let us find the f of b, wherein b is 1 and 3. Okay? So, the first one is f of x. Let us have our function. And f of a is equals to this to our function. And let us substitute the f of a, which is 1, the a, which is 1, to our function. So, let's have f of 1 is equals to 1 cubed plus 1 squared minus 2 times 1. And the answer is negative 2, because 1 plus 1 is equals to 2. No? 1 plus 1 is equals to 2 minus 2. Alright. So, let us have the f of x equals, let us have the f of b. Let us substitute the b value, which is 3. So, we will have f of 3 is equals to 3 cubed plus 3 squared minus 2 times 3. We will have the f of 3 is equals to 12. Then, we can now solve for the value of c. So, since our f of 1 is equals to negative 2, and our f of 3 is equals to 12, no? So, let us use the mean value theorem. F of 3 minus f of 1 all over 3 minus 1. Our f of 3 is equals to 12. So, 12 minus our f of 1, which is negative 2. So, 12 minus negative 2 is 14 all over 3 minus 2, which is 2. So, 14 minus 2 is equals to 7. So we set the f prime of c is equals to 7. So, to obtain, so we have 3c squared minus 2c minus 2 is equals to 7. So, 3c squared minus 2c minus 9 using the subtraction property of equality, no? So, using the quadratic formula, which is, we could obtain using quadratic formula, this one is a quadratic formula, no? So, we can obtain c is equals to 2 plus square root of 112 all over 6, and another c, which is the 2 minus square root of 112 all over 6. So, the first approximation is the c is equals to 2.10, and the second one is c is approximately negative 4.3. So we're going to find which number, no, c in the open interval will satisfy the mean value theorem. So because 1.3 is not in the open interval 1, 3, the only possible value for c is 2.10. So the figure 1 below, which is right here, no, shows that the graph of f the tangent is x is equals to 2.10, which is right here, right there. And the secant line through the point 1, 1, 1, negative 2, and 3, 12, right there. Plotted and 0 in the interval I use is 0 and 4 by 0 to 5. The fact that the tangent line is parallel to the secant line supports the choice that C as 2.10. So let us have another example to furtherly understand the mean value theorem. Okay, what is it again? The mean value tells us, no? The mean value theorem tells us that there is a point where the tangent line is parallel to the secant line. So let us have the example number 4. The f of x is equal to x cubed plus x squared minus x in the closed interval, negative 2 and 1. So our task here is we have 3, right? So let us verify the two hypotheses of the mean value theorem indicated in the interval AB. Then let us find a suitable choice for C that satisfies the conclusion of the mean value theorem using the mean value theorem, of course. Support the choice of C by plotting in the same window the graph of f on the closed interval AB, the tangent line C, f of C, and the secant line through the point f of A, B, f of B, and observing the tangent line and secant line are parallel. You may pause the video if you want to join. So let us have the solution of the example 4. Let us first, right now, verify the two hypotheses or the two conditions of the mean value theorem. So, because f is polynomial function, therefore it is continuous everywhere. Thus, it is also continuous with the closed interval negative 2 and 1. So, let us know if it is also differentiable everywhere or in the open interval negative 2 and 1. So, let us have f of x is equal to x cubed plus x squared minus x. Let us find the f prime of c or the f of x also. So the f of x is equal to 3x squared plus 2x minus 1. So it is differentiable everywhere as shown here. Thus it is also differentiable on the open interval negative 2 and 1. So let us have the letter B. We're going to find the suitable choice of C that satisfies the conclusion. So, letter B. By the mean value theorem, there exists the number C in the open interval 0, 1 such that there exists a number in C 0 in the open interval 0 and 1. So let us find the value of C. So the value of C is that we use the mean value theorem, which is what is the mean value theorem again? So the mean value theorem states that the f prime of C is equals to f of B minus f of A all over B minus A. So let us use that formula. So the f prime of C is equals to f of 1 minus f of negative 2 and 1 minus negative 2. We all know that that our A and B is 1 and negative 2. Therefore, fc squared. So we know that the f prime of C is already 3c squared plus 2c minus 1 is equals to 1 minus negative 2 all over 3. So this one, no? Right here. 1 minus negative 2 all over 3 is equals to negative 1. So using the property of equality, right? So we could have 3c squared plus 2c minus 2 is equals to 0. So, we could, using the quadratic formula from this one, no? We could obtain that we could have the c is equals to 1/3 of 1 minus 1, negative 1 rather, plus square root of 7, or approximately 0.55. And c is equals to c for the negative side is 1/3 negative 1 minus square root of 7 is approximately equal to negative 1.22. So the next is to support our choice by plotting in the same window. So by the graph, no, it tells us that there are points. Okay, wrong. So there are points where the tangent line is parallel to the secant line. So this is our tangent line, this one right here, and right there, which are the point negative 2 1 point rather, negative approximately negative 1.22 right here, and approximately 0.55, which is right here, that is parallel to our tangent line, which is the a f of a and b f of b. So let us have another example. Okay, sample number 5. Let us have the function f of x is equals to 1 to minus the absolute value of x in the closed interval negative 1 and 1. So the same rule, we're going to verify the hypothesis of the mean value theorem. Those are two, right? Then find a suitable choice of c that satisfies the conclusion of the mean value theorem. And we're going to support our choice by plotting in the same window the graph. No? So, you may pause the video, want to join and to answer this one. Okay. So let us have the solution now for the example number 5. The first task that we have is going to verify the two conditions, no? Because f is a polynomial function, it is continuous everywhere. Thus, f is continuous in the closed interval negative 1 and 1. Then, for the number 2 tells us that if it is differentiable in the open interval. So, remember that our function earlier is an absolute value, right? 1 minus the absolute value of x. So, the absolute value is not differentiable at 0. F is no differentiable on the open interval negative 1 and 1, and thus the second condition is not satisfied. Therefore, there is no suitable choice of C that satisfies the conclusion of the mean value theorem. Why? As I said, no, since the condition 2 is not satisfied, thus, there is no suitable choice for C that satisfies the conclusion of the mean value theorem. Let us show the graph, no, to furtherly understand that there is no point. There is no point in which the tangent line is parallel to the secant line. Right here. Because one of the conditions of the mean value theorem is not satisfied, we cannot conclude that there is a point at which there is a horizontal tangent line. Indeed, as the figure on the left side illustrates, there is no such point. So, allow me to recap our topic, the mean value theorem. So, for the lesson closure, the conclusion of Rolle's theorem states as what? And the mean value theorem states as what? Alright, so let us have the lesson closure. The Rolle's theorem states that on the graph of f, between the point where x is equals to a and x is equals to b, there is a point at which the tangent line to curve is horizontal. The conclusion of the mean value theorem states that on the graph of f, between the points where x is equals to a and x equals to b, there is a point at which tangent to the curve is parallel to the line joining these points. Note that the Rolle's theorem is actually a special case of the mean value theorem. The mean value theorem is among the most important theorems of the calculus because it's used in the proof of many theorems. So let's do it, and let us have a formative exercise to test your knowledge about the mean value theorem and also for the Rolle's theorem. You may screenshot the screen. For the exercise 1 through 5, verify the three conditions of the Rolle's theorem. What are those? I already discussed it. Are satisfied by the function, and if those three conditions are satisfied, you may find the suitable value of c that satisfies the conclusion of the Rolle's theorem in the closed interval of the given function. For letter V, so for the exercises 6 through 9, let us verify the hypothesis of the mean value theorem. Those are two, indicated in the interval AB. Then after that, you may find the suitable choice for C that satisfies the conclusion of the mean value theorem. And after that, you may support your choice by plotting the C, on the same window of the graph. You may screenshot for the item 6 to 9. Okay, let us have letter C. Then for each of the function exercises 1 through 4, there is no number C in the open interval AB that satisfies the conclusion of the mean value theorem. In each exercise, you are going to determine which part of the hypothesis of the mean value theorem fails to hold. So after that, you may sketch the graph of F and the line through the points A and F of A and B, F of B. So on this part, you're going to determine which part of the hypothesis of the mean value theorem fails to hold. You may screenshot this one. And let us conclude everything. So lesson closure. I've already tell you this one also, the Rolle's theorem. There's a point at which there is at least one point at which the line is tangent to the curve is horizontal. And the mean value theorem states to us that there's a point at which tangent to the curve is parallel to the line joining these points, which is the second line. Note that Rolle's theorem is actually a special case of the mean value theorem, and the mean value theorem is among of the most important theorems of the calculus because it is used to prove many theorems such as the intermediate value theorem and there's also another one. The intermediate value theorem and extreme value theorem. So if you have questions and further clarifications, you may drop it in the comment section. That's all, and may you have a great day ahead, and God bless.